Thank you very much. Good afternoon. Today I'll present our paper on our software system, Python-based by the name of RLgraph. And it's, with RLgraph, you can build and execute modular computation graphs for deep reinforcement learning. This is a collaboration with Michael and Eiko from the University of Cambridge, as well as Kai from HSU Hamburg. Before we talk about RLgraph, let me quickly recap what reinforcement learning is. In reinforcement learning, we have a dynamic environment which produces state and reward signals. These signals are picked up by our agent, by our reinforcement learning algorithm, which then maps these signals to action outputs, and these actions are applied to the environment, and the environment reacts via its underlying rules and physics based on these actions, and it outputs new state and new reward signals. So this is an ongoing iteration. It can go on for some time, and the goal of the agent is to maximize over its lifetime the total sum of individual reward signals. What are the differences between supervised learning and reinforcement learning with respect to workloads and execution patterns? In reinforcement learning, we have this constant requirement of collecting data while we learn. So this has to happen simultaneously to learning. We cannot collect data first and then learn and we're done. This has to happen at the same time. One way of doing this, of speeding up this process of data collection, is to parallelize the environment and then to drop special agent copies into these individual environments to collect samples. So this then brings the need of data exchange. So you need to send trajectories, episode trajectories from the individual environments up to the centralized learner or learners. There could be more than one. And on the other hand, you have to send down or synchronize down the neural network weights and parameters to your environment workers from time to time to keep them updated. This is one reason why reinforcement learning workloads are complex. There are a lot of different ways of how to do this. And another important difference between RL and supervised learning is the fact that we don't have labeled data sets. So we have to work with, often with very low quality reward signals, could be sparse or delayed. And this leads to instabilities in the learning process. Our loss functions are more bootstrapped than the supervised ones. So all in all, reinforcement learning is even more sensitive to hyperparameters than supervised learning. There are a number of existing libraries and reinforcement learning algorithm implementations available. They offer good results on select environments, and of course they provide concise code references on a per algorithm basis. What we did find was that often they're hard to retool to other environment types or to different execution modes. So there's no simple switch that you can flip to make a single-threaded algorithm run in distributed mode or in multi-GPU mode. And this is the part of the reason for that is that there's a lot of implicit dependencies between parts, which then also leads to limited testability. So you cannot take out a component from this code and test it as such, as a single component, or take out two components and test them together and in combination. So this leads to limited testability, and also often they're restricted to single backends. So it's either they support TensorFlow or PyTorch. Some of them have a set of algorithms that runs on TensorFlow and a set of different algorithms that runs on PyTorch. You see a list here of the other methods that we mentioned in the paper, and there's actually more. You can go to the paper and check out the discussion on the related work. What does RLgraph do differently to address these issues? We have so this is basically the bottom line of today's talk. We separate concerns. This is our design stack, and we're going to go step by step through each of these layers in the following slides. Just to give you a quick overview, we have a top-level API, and this is the API that the agent uses to step through the algorithm. So it's usually a handful of methods that you can call, and this is what you would use if you just want to use RLgraph to solve your problem with an off-the-shelf algorithm of ours. Underneath that is what we call the abstract data flow definition layer or the component graph layer. In this layer, you would operate if you would design your own algorithms. And here you define in a very abstract, high-level way how data will flow through your computation graph. So you basically hash out the basics of your algorithm. And separate from that, we have the local backend layer. So we support TensorFlow and PyTorch currently. meaning both paradigm static graph as well as defined by run. And the TensorFlow and the PyTorch code is nicely encapsulated in special functions, so you can easily in the future add support for a third backend, such as TensorFlow 2.0 and others. Again, separate from that, separate from the local backend layer, is the distributed execution layer. We support also here different engines, distributed TensorFlow as well as Ray. And of course, RLgraph runs on all hardware. So let's go step by step now through the different design layers. Top-level API, our agent has a root component, and each component has an API. So we define very shallowly 3 methods that the agent will need to step through the algorithm. For example, update to learn something, observe to push data into the memory, and act to step through the environment. And now we're going to create subcomponents, and we're going to place these subcomponents into the root component. So these are the components that we need to execute the algorithm. We need an optimizer. These are simple Python constructor calls. You pass them some configuration parameters as constructor arguments. You create an optimizer, you place it into the root component. You do the same. We also need a neural network. We need a loss function, and we need a memory. Note here that some of these subcomponents that you're placing into the root have their own subcomponents whose API they can use. So each component has an API, and it can use and call its subcomponents' API methods. And again, the agent only has access to the top-level API. So you end up with an arbitrarily nested component tree without, so far, any connections between the components. The connections we're going to make now in the next layer, where we build the component graph. And we do this, again, in a very abstract way. So this is the step where you abstractly define how data will flow through your algorithm. So let's say we take the update method, and we define that it will call the sample method of the memory component. It gets an abstract data record back. It pushes that through the neural network. Again, gets an abstract data record back, pushes it through the loss function, and then we do the optimizer step. So this is how you hash out in a very high-level abstract way, using simple Python code, how your algorithm should work. Again, we have no shape data at this moment. We have no idea what our data types are or whether it's batch data or not. The very abstract layout of the algorithm. At this time, you can, if you have multiple GPUs, you can tell RLgraph to restructure this idea of the algorithm to make the same algorithm run with multiple GPUs. And it will automatically create the GPU towers. It will automatically repipe everything and then make sure that the algorithm that you defined here runs on multiple GPUs. The next layer is the local backend layer, and now we get to the actual, what we call the build process. So here we do have to define input spaces for the first time, only for the outermost component. The following steps are all automated, so all you have to do here is call agent.build. And it will basically trickle down in an iterative build process these placeholders, create tensors out of it, and push them through the components in exactly the same way as you have defined before, in the step before when you did this abstract data flow definitions. We have the concept of component readiness. So a component is ready when it knows its input spaces. And when it's ready, we assign explicitly and automatically devices to the entire component. We assign scopes. We create and share variables for the component, sharing, of course, optional. And we call the components computation functions. And while these spaces and tensors are trickling down the components, you get intermediate spaces which are inferred automatically. And eventually you call these computation functions here. So in case of TensorFlow, this means that right now you're building your static end-to-end graph. And in case of PyTorch, this means that right now we're doing test calls with dummy tensors through the defined by run functions to make sure everything is wired correctly. And if it's not, you get meaningful error messages. So you end up with some output for this particular update API method. So this component-wise approach allows us to create really nice visualizations of the computation graph. This is a tensor board visualization of our IMPALA algorithm. And you get this off the bat just by using RLgraph. So you define your abstract data flow with RLgraph, and then you say agent.build, and you get this exact tensor board graph. So you can see nicely here each component. You can see where it's placed, and you can see the data flow really nicely between the different components. So it's very good for debugging. This is a comparison to when you use direct TensorFlow scripting. This is DeepMind's IMPALA repository, the reference implementation of IMPALA, where they're using direct TensorFlow scripting and Sonnet. So you can see it's much more dispersed. You would have to put in a lot of work, manual work, to make it look like ours. Fourth layer, we have the distributed execution engine, and again, it's separate from the local backend layer. So this is a diagram of our build and execution process. What we talked so far about was the first, the yellow section here, and now you can basically plug in your distributed execution engine. We support both Ray and distributed TensorFlow, and you can actually combine. So if you have a local TensorFlow agent, you can run it in distributed mode using Ray, or you can choose distributed TensorFlow. You cannot combine a PyTorch, local PyTorch with distributed TensorFlow, of course. That's the only combination that doesn't work. Quick intermediary summary, RLgraph is a programming model to design and execute reinforcement learning algorithms in a backend agnostic fashion. RLgraph generates incrementally testable, transparently configurable code through a strict build process. What does incrementally testable mean? It means that you can take very simple components and test them end-to-end as your entire algorithm, basically. And then you take more complex ones, composed of these simple components, test them end-to-end. We have over 300 test cases. We test all our components and abide to very strict software development standards. RLgraph offers a high-level API for practitioners, so you can use our algorithms off the shelf and run them right away on your problem domain. And for researchers that want to develop their own algorithms, most of the time you operate in the first two layers, top-level API as well as abstract data flow definition. Evaluation, we ran a couple of experiments to ascertain learning capabilities as well as runtime and build time performance in terms of speed. So this is the first experiment. We measured the build time overhead. So basically, how much time do you add when compiling your graph using RLgraph versus not using RLgraph? We tested both backends, TensorFlow and PyTorch. There's two sections here. Dataflow is the second layer where you define your abstract data flow, and build is your the actual build process where you build the static end-to-end graph. DQN is a full-blown algorithm with 60 components. Network had over 1 million weights, so it took less than a second to build this, it took less than a second overhead to build the graph with RLgraph. Compare this to the execution times of many hours when you run reinforcement learning experiments on a lot of environments. This is really, no real overhead there. Next, we measured the runtime overhead. Here we used the Pong environment, which is an Atari-based, image-based game environment. And in this experiment, we just did stepping. So we wanted to know how fast can our algorithms step through the environment. So there were no learning updates done in this experiment. We measured against different numbers of vectorized environments on a single threaded worker. So it's a single worker that operates on many environments in parallel, gets many state signals. So it's basically the batch size, the state batch size, and it outputs a batch of actions. You can see here that the interesting here is for PyTorch you have a slight overhead RLgraph versus the hand-tuned one, which hand-tuned means without RLgraph. This is due to the fact that for the execution time in PyTorch, there is some overhead because we're doing additional function calls. For TensorFlow, it didn't matter. That's why you only see one curve here, the red one. Because for TensorFlow, after the build process, you end up with a fully qualified end-to-end graph, and there's no difference whatsoever between using RLgraph and not using RLgraph. So it performs just as well as direct scripting. Next, we tried to learn the same environment, so we tried to solve it basically. So again, this is the Pong environment. On the y-axis, you have minus 21 means you have not learned. You're basically acting randomly. You lose all the time. And plus 21 means you mastered the environment. You win every single game against the computer player. You can see here, this is with our Apex algorithm, which is a distributed flavor of the DQN algorithm. Our line is the blue one. You can see that we learned the environment in less than 2 hours using 32 workers and 1 GPU. And we compare this to the Backend state-of-the-art reference implementation of Ray RLlib. The reason why we're faster here, why we're learning faster, is because we found we did a thorough analysis of each component for the entire graph pipeline, and we found that we could save a lot of time on reducing session calls. So we batched together the post-processing data that were collected by the different workers, and we were able to cut down the number of session calls. That was the main reason. We found many other components that had slight optimization potential, and we exploited that. This is the same experiment using 2 GPUs. So this is basically, the blue line is the same as before, and the green line now shows the same agent, but with 2 GPUs. Using the before mentioned system for rewiring and creating these GPU towers, which is done automatically for you by the library. So you can see that almost the speed up is significant. It doesn't quite perform twice as fast, but of course there's always some overhead when you have multiple GPUs. Last experiment, this is using the IMPALA algorithm on a different environment, DeepMind Lab. It's a three-dimensional environment where you also have images as well as a text stream. So you have to process both, and you have to navigate through this three-dimensional maze and avoid certain items and collect other items. In this experiment, we did acting as well as learning updates, and again, we measured the environment frames per second using different number of parallelized workers. You can see that we couldn't really perform faster than the DeepMind reference implementation. This is mostly due to the fact that this is a fully TensorFlow end-to-end algorithm where even the environment interaction is fused into the graph using a TensorFlow PyFunc operator. Lastly, summary and outlook. Reinforcement learning workloads are hard, and we need new programming models. RLgraph enforces a strict build process, and it separates concerns. And we focus on data flow composition, not backend specific code. For the future, we will look at integrating RLgraph, which we'll hear about in a second in the next talk, I think, or in one of the next talks, as well as for PyTorch JIT tracing. And our code is available as open source under the Apache license on GitHub. Please check it out. Thank you so much.
Please come to the mic if you have any questions.
Hi, Ash Unity. Super cool work. I had a question. So does your framework make any assumptions in terms of the API to the environment?
No.
Okay, so I could possibly have an environment that relies heavily on a GPU but has a GIM interface, for example.
Yeah, correct. We have several adapters implemented that you can use off the shelf. OpenAI GIM, of course, is one of them.
Okay.
Of course, you have to be, some environments have some crazy state space, right? They give you a dictionary, then you have many flows, many streams of data. Like this IMPALA, DeepMind had an image stream and a text stream. So, but in general, the agents, and when you create these abstract data flows, it's independent of that.
Okay.
Yeah.
But I assume that I would have to manage which GPUs the environments run on, as opposed to, I guess, allocating some GPUs for RLgraph?
You wouldn't, yeah. So far, we've experimented without GPUs in the environment. So our workers run on CPUs, and we use only GPUs for learning. So the experiences, the trajectories are sent to the learner, and then the learner has a GPU, and it takes the experience and learns from them. But for environment interactions, we haven't used GPUs. That's actually an interesting question. You're asking probably because of the game engine, right?
Yeah.
It's an interesting question, and we haven't done any experiments on that.
And I guess one thing I'd be interested in is the kind of thrashing that happens when the game engine wants to use the GPU, and then you're flushing the data out of the buffer back into the CPU memory, and then the learner takes over and
yeah.
the stuff that happens there.
Yeah.
The other question was a technical point on your comparison between RLgraph and RLlib. Was the execution engine for RLgraph Ray in that case?
Yes, correct. Yeah, correct.
Okay, cool.
So yeah, so basically both use Ray. Yeah, that's right.
All right, awesome. Thank you.
Yeah, sure. Thank you.
Great. Let's thank Sven again.
Thank you. Thanks a lot.